Hello and welcome to the second installation in our lecture series. Today we're going to be talking about the basics of quantum mechanics. So the topics that will be covered today are what are quantum states, how do we measure them, and how do they evolve? So what is a quantum state? A quantum state is basically the probabilistic state a particle is currently in. Now, in classical mechanics, when I measure something, let's say I'm measuring whether a coin is up or down. The coin is either in a deterministic up or down state before I've looked at it. It's either up or down. Now, in quantum mechanics, we don't make the assumption that the coin is in one of either states. Instead, we say that the coin is in a state which is represented by a probability distribution of it either being up or down. So we could have it being in the distribution of having 100% of it being up, or the opposite. You could say that it's 100% down. Quantum mechanics also allows for the cases of it being, for example, 50% up or 50% down. Now, does this mean the coin is either up or down? Neither. It's in this state of being of if of being 50% of the time up, 50% of the time down. So if I measured this coin 100 times and it was paired in this state every time, I would get 50 up cases and 50 down cases. Now, how do we represent these quantum states, these probability distributions? Well, we represent them by vectors in what's called a Hilbert space. Basically, a Hilbert space is the set of quantum states. And the nifty thing about Hilbert spaces is that they can be represented as the linear combination of these basis vectors. So if I have a quantum state, all I need to know is what are the coefficients that I multiply to each basis vector. And actually, these coefficients represent the probability. So the probability would be the absolute value of the coefficients squared. So these coefficients can actually be complex. And that's the unique thing about quantum states. Now, for each quantum state, I have a corresponding dual vector, which is basically if I have a corresponding ket, I also have a corresponding bra. And that's just a complex conjugate of the quantum state. Now, if I were to multiply these through an inner product, I would get 1. Why? Because if I define this to be the probability, and I work through the algebra, I would end up with this quantity right here. And this quantity, being the sum of the probabilities, always has to be 1. Now, we can't actually derive this. This is basically just a definition. And these are this is the playing ground we're starting with when we're doing quantum mechanics. So just to give a short example, let's say we have a oscillating electric field, i.e. light, basically in layman's terms. Now the light is moving one direction, z, and the direction in which the light waves wiggle, the electric fields oscillate, is called the polarization. So we can have it wiggle from side to side, or up and down, or a mixture of these two, for example, a diagonal. So let's say I have unpolarized light, which means it wiggles in every direction equally, and it passes through this polarizer, this horizontal polarizer. This only passes through light that's going in the horizontal direction, that's polarized horizontally. So the result would be horizontally polarized light. Now, if I were to try to pass this through a vertical polarizer, I would get no light at the end. But let's say instead I insert this diagonal polarizer before giving it to the vertical polarizer. What would happen? Well, this horizontal polarized component can be written as the sum of these two diagonal direction, aka the superposition in fancy terms. Now, superposition is a term that's used a lot in quantum mechanics. That leads to some people thinking that it originated from quantum mechanics, but this is actually a term from wave mechanics. Because another name for the quantum state is actually the wave function, which is a testament to its non-binary nature. So we have a superposition of these two directions, and we pass it through this diagonal filter, which filters out only this direction. But this direction can also be written as the horizontal and the vertical directions. So we end up with a vertical component at the end. Now, this can be written in the language of quantum mechanics via these vectors, these quantum states. So this diagonal vector could be written as the state, the superposition of the horizontal and the vertical vectors. And the horizontal state can be written as the two diagonal vectors, and vice versa. So the moral of the story is that there is no unique way of representing quantum state. The same quantum state, for example, the horizontal vector can be written as either this or this. There's no unique way of looking at a situation, a vector. It depends on what basis vectors you use, but they ultimately point to the same quantum state. Now let's talk about measurement. Now, how do I analogize quantum states with classical states? What's the difference? Well, this is where measurement comes in. Now, the physical thing we actually see is not the quantum states, but the classical products of measuring a quantum state. So when I measure a wave function, and this wave function was represented, for example, I get not the wave function itself, but I can measure each and every one of the outcomes. So the basis vectors can also be thought as different outcomes of measuring the wave function. And how you measure it determines your basis vectors. So these are the outcomes. And A0, A1 squared. These represent the probabilities, basically. So we have a wave function, and we're going to measure it. How do we represent this in the language of mathematics? Every measurable physical quantity is described by a Hermitian operator, which we learned in lecture 1. A acting on the state space, H, basically the Hilbert space. Now, this operator is what we call an observable. And why it should be an Hermitian operator is because the eigenvalues are real. And these eigenvalues, they represent the physical quantities we actually measure when we're measuring an observable A. So when we try to measure an observable A in a system, the probability of obtaining the eigenvalue is given by the amplitude squared of the appropriate wave function. So in more complex terms, in mathematical terms, if I have a wave function here, psi, and I applied what's called a measurement operator, this basically collapses this into one of the outcomes. And then this constant is there for normalization to ensure that the inner product is 1. The size, the magnitude is 1. So when you're measuring a quantity, this is mathematically what you're doing. You're just applying a measurement operator on the original wave function, and this measurement operator turns this into either one of these outcomes. And this quantity here actually represents the probability. Okay. So let's look more into the eigenvalues. How do we find the eigenvalues of observables? Now, the neat thing is about Hermitian operators is that 1, the eigenvalues are real, and 2, the eigenvectors form what's known as an orthonormal basis, which basically means that their size, their magnitudes are 1, and they're orthogonal with each other, which makes them easy to deal with. So, since they also form a basis, every single vector in Hilbert space can be written as a linear combination of the eigenvectors, which means that if we move onto the spaces, if we use the spaces, we can write our Hermitian operator like this, basically, as a diagonal matrix. And this is also called diagonalization. So here's a short proof of that, basically. And then basically what we're doing is when we measure something, we're actually measuring one of these eigenvalues. So measurement outcome. So let's look at another example. Here we have this quantum state psi, which is comprised of alpha and beta for each of the amplitudes. And then we have this observable on our two-dimensional Hilbert space, 0 and 1, which has these different outcomes, lambda 0 and lambda 1. Now, the probability of observing lambda 0 for our observable A is going to be alpha squared. And the probability for lambda 1 will be beta squared. Now, this is obviously easy to see because they're in the same basis. But what if they're not in the same basis? What if we only had psi in one basis and we diagonalized A in another basis? How would we calculate the probabilities here? Well, if you think about it, basically, what we're doing here is we're calculating what's called the expectation value right here. So let's say that we have our observable A. And then we apply this observable onto our quantum state. Now, we choose to take the inner product with the quantum state again. Now what we're doing is this gives us, this half gives us basically this quantity, which is the outcome multiplied by the amplitude right here. And then if we take this product, we also get these cancel out to give us the probability squared of lambda 0, lambda 1. And since this is the probability and this is the outcome, this is the probability, and this is the outcome, this is what we call the expectation value. Or basically the mean. So finally, to wrap up our lecture, how do closed quantum systems evolve? How do our quantum states evolve? Well, in technical terms, the evolution of what's called a closed quantum system, basically no interaction with outside world, is described by what's called a unitary operator, which we learned in lecture 1. Now, why are they described by unitary operators? Well, if a wave function turns into another wave function, what must be the same is that the norm must be still equal to 1, because all probabilities must add up to 1. So let's say we don't know if we describe the evolution by this matrix U, then taking the inner product with itself gives us this quantity right here. And this quantity needs to be equal to 1. So this means that it needs to be equal to the identity right here. Because for every U, this needs to be satisfied for every U, which is basically the definition of unitary matrices. So for example, let's say we have two qubits, two states, 0 and 1. And we have this operator X. Now, the Hermitian of X is basically itself. And if you do some matrix product, we get I, which means it is unitary. And if you apply X to 0, what we get is 1, and vice versa. This is also called the bit flip operator, or the Pauli X operator. Another example of a unitary operator is what's called the Hadamard. Hadamard operator, or gate 1. If I apply this to state 0, what I get is, and multiply these terms out, is this a superposition of 0 and 1, equal probabilities. However, for H1, I'll leave that up to you for you to figure out. But it's another superposition of 0 and 1. So the Hadamard gate can be used to create superposition. Now, this all culminates in what's called the Schrödinger equation. Basically, what this equation basically tells us, what is the actual form of U? Schrödinger equation basically tells us that the rate of change by time of the wave function is governed what's called the Hamiltonian. And the solution to this Hamiltonian is actually given by a unitary matrix applied to the initial state, which is a state at t0. The closed form of this is actually this. Well, this wraps up our lecture on the basics of quantum mechanics. I hope you enjoyed the lecture, and I'll see you next time.